Okay, now another thing about these Lewis structures is that they're great for helping us understand who's bonded to who, and it's a model we use to represent the molecule. But sometimes the model just doesn't quite work as well as we would hope. So let's talk about what we call resonance structures. Okay, what are resonance structures? Well, I have a molecule, and I'm trying to draw the Lewis structure to represent that molecule. Lewis structure is just a model. And I'm trying to draw a Lewis structure. But one Lewis structure doesn't quite capture what the molecule really looks like, So what I have to do is draw 3 or 2 or however many number of Lewis structures I need to represent what that complete molecule really looks like. Okay, so for example, let's say we've never met Bryn. We don't know what she looks like. Okay, never seen her before in our life, right? And then you had to pick her out of a crowd. And if I just showed you the backside picture of Bryn, just from behind, yeah, there you go. It would be really hard to pick her out, wouldn't it? And she's not just a flat back picture, is she? No. So what if you saw the back side? What if you saw the side profile and the front profile? Then you get an idea of what she really looks like? Yes. Okay, so it took 3 pictures, didn't it, to really help us understand what Bryn really looks like. And there's only one Bryn, okay, just one. But it took 3 pictures. That's what we're talking about with resonance structures. I'm going to draw multiple resonance structures to represent only one structure. And what I'm trying to do is show what that one structure really looks like. So what's the difference between these resonance structures is what we call them. These resonance structures differ only in the placement of the electrons. Okay, the central atom is still the same, all that other peripheral atoms is still the same. We're only talking about the difference in the placement of electrons. So you'll be able to pick out how many resonance structures there are. And remember, these resonance structures shows what that molecule looks like. So it's actually a blend of all 3, just like Bryn is a blend of all 3 of the pictures. So let's go and let's do carbonate, CO3. Okay, so we're going to do CO3 2-. So let's draw the Lewis structure for CO3 2-. So I have a carbon, an oxygen, another oxygen, another oxygen. I draw in the single bonds, complete the octets on all of these. This is my Lewis structure for CO3, but carbon does not have a complete octet, does it? No, it only has how many? 6. Okay, so I'm going to need to add something to that. So what I would do is what? Rearrange, get a double bond. Okay, well, which oxygen are you going to use the double bond with?
The top one.
The top one. All right, let's do the top one. Okay. All right, well, there we go. Well, you know what? Maybe we didn't want to do the top one. Maybe we said, hey, let's do the side one. So let's put our Lewis structure back up here. And let's say, hey, I'm going to use the side one. All right, so let's take this one off. Put a double bond there. Oh, what if it's not that side that we wanted? What if it's the other oxygen? Okay, well, let's draw another one. Okay, so here we go. Another one. And this time we're going to use this one on the right and put a double bond there. Wow, I've got 3 different structures. How do they differ? That's right. It differs by the double bond, the placement of those electrons, doesn't it? That's the only difference. Okay, great. Oh, that should be a 2-. So, wow. Well, which one is it? It's actually all 3. We're like, what? So where's the double bond? The double bond is actually spread out over all the oxygens. Yeah, that's kind of hard to understand. And we're like, how am I going to show that on a Lewis structure? That's really difficult. And when we talk about our molecular models, we'll understand this and be able to, some other models we're going to talk about to help us understand this idea of what this one molecule looks like. This one molecule has that double bond spread out over all 3 oxygens. So how are you going to represent that with a Lewis structure? Do we see the limitations of our model? So what we're going to do is draw 3 pictures. These are called resonance structures. And then I'm going to put a double-headed arrow like this between there. And what that means is all 3 of them represent one molecule. That double bond is not flipping back and forth and switching. It's not switching back and forth. Okay, it's not doing that. It's a blend of all 3. Okay, so that's what we're talking about with resonance structures. And you can recognize that because of the opportunity to place the electrons in a different way, like that. Okay, here's another example of resonance. Sometimes you might have 3, sometimes you might have 2. So in this case, this is ozone. So notice the difference between these. I had a choice of where to put that double bond. So in this case, I had 2 choices. So I have 2 resonance structures. So where is the double bond really? It's over both of them. Okay, and again, there's that arrow like this. Not the dynamic equilibrium arrow, but this one. As that means resonance structures. Okay, so that's ozone. That's another resonance structure. What about benzene? This is benzene. Ooh, can you tell the difference?
Pretty.
Yes, it's pretty. What can you tell the difference between these? Is the placement of that double bond again? Everybody see it's a little bit slightly different? Okay, well, we can represent these structures. For those of you that are going on to organic, you'll represent them as geometric shapes. So do you see where each point is a carbon and we didn't put the hydrogens? We're just representing this as a geometric shape. So you see where we put the double bonds?
Yeah.
Okay, they're slightly different. Well, in this case, I have 2 resonance structures. Where is the double bonds really? Where is those double bonds? All over. So I'm just going to draw a circle. And that represents that. So you might have seen this structure before. Well, that circle means resonance. And because of the resonance where that double bond is spread all the way around, it makes this structure extra stable. It does have double bonds, but it doesn't behave like other compounds with double bonds because of that extra stability. We call that delocalized electrons. They're not stuck in one spot, but they're spread all over. So Kekulé, who's trying to figure out this structure, he is having such a hard time because of the resonance that was involved. And he said as he was studying his chemistry by the fire, he started to doze. Now, you guys are never going to doze when you're studying your chemistry textbooks, right? I know that, right? Okay. Okay, so he's starting to doze by the fire. And when he fell asleep, he said in his dreams he saw a snake whirl around and grab his tail. And it whirled around. So then he woke up and he drew the structure. And that's how he got the structure. So the next time, take a nice, good night's sleep, and maybe you'll dream all the answers to the next test, right? All right. Yeah. Okay. Yeah. I know, it's awesome. I know. Okay, so do we understand resonance? We can recognize resonance, right? All right, so far, everybody can draw Lewis structures. We can do multiple bonds. We can do formal charges. We can do resonance. We're getting so good at this, right? It's awesome. Okay, well, what we were doing was so easy. So, yeah, let's do something else. Yeah, let's just stop here. No, okay, you know how we were talking about our steps, and we said, oh, complete the octet, complete the octet, complete the octet. Well, now let's talk about the exceptions to the octet rule. Yeah, and we need to know the exceptions to the octet rule. Yeah, we do. And be able to recognize them anytime we see them. So these are the exceptions to the octet rule. Now, we can have more than an octet, we can have less than an octet, or we can have an odd number. Whenever we have these instances, there won't be a complete octet. We can't complete the octet with 8. So let's talk about all these individually. This is an odd number of electrons. So let's talk about this, an odd number of electrons. Well, what's an odd number of electrons? Well, somebody's not going to have an octet. For example, nitrogen and oxygen. Okay, nitrogen has how many valence electrons? Nitrogen has how many valence electrons? 5. Oxygen has how many? 6. That's 11. Okay, somebody's not going to have an octet. Okay, so that happens sometimes, and that's rare, but it does happen. Have you ever heard the term free radical? Yeah, that's what we have. That's what we got going on here. Is a free radical. It's got the unpaired electron. It's like, ooh, I want another pair. I want another buddy. So I'm pretty reactive. I'm just going to do what it takes to get one. So free radicals tend to be very reactive because they want to finish off that pair. And so have you heard the term free radicals, and you're eating in your body free radicals cause unwanted reactions? So what do? You eat what? Antioxidants. What does the antioxidants do? Mops up the free radicals, right? So where do you go to eat antioxidants? Pharmacy. Fruits and vegetables, right? So here's a plug to eat your fruits and vegetables. Yes, let's be healthy, eat our fruits and vegetables. You'd rather go to the pharmacy. All right, well, how about less than 8? You guys know less than 8 already. We've talked about one element that can only have 2 electrons. Which one was that? Hydrogen. Remember hydrogen? Less than 8. Well, that hydrogen's not the only one. There are a few others, and you do need to know those. For example, if we drew the structure for BeCl2, okay, BeCl2, beryllium has what? 2 valence electrons. Each chlorine has 7. Okay, so we would look at that and say, oh, 14, 15, 16, and then we would draw that Lewis structure with beryllium in the center, single bond to a chlorine, and then our valence electrons around the chlorine, and that's it. Am I going to say, oh, beryllium should have 8 and try to do double bonds? No, you're not. Okay, so don't do that. Don't forget about these and try to do multiple bonds with beryllium, boron, or aluminum. Okay, if you did the formal charges, you'd see that doesn't work out so well for beryllium. So don't do that. So you're going to need to remember that these are happy with 4 and 6 or 2 electrons. Don't try to do multiple bonds with these. Okay? All right, so that's an example of less than 8. And now the next one, which is the biggest example of them all, they have more than 8. This is the largest group of exceptions, more than 8. So who can have more than 8? Well, it's the third row. So look where we are on the third row of the periodic table. Starting in the third row, and everybody else on down. So we're like, whoa, that's a lot. So, there's only a few that have 8 always, right? Okay, so third row on down. Now, valence electrons are the ones that do the bonding. They're the ones that do the bonding. Okay, so let's think back to electron configurations. 8, okay, that makes S and P electrons, right? S and P orbitals. Those are the outer shell. Well, didn't we say D can sometimes act like valence electrons and sometimes act like core? So when we have more than 8, that means the D electrons are getting involved. And where is it that we have the D orbitals? Is it the 1, shell 2, shell 3? Where do we get the D orbitals? Shell 3, right? Because shell 1 has S, shell 2 has S and P, shell 3 has S, P, and D. So that's why the third shell on down can have more than 8, because we got those D electrons going on in there, don't we? All right, so let's take a look at some cases where we have that. Let's take a look at phosphorus. Phosphorus, is that in the third shell and on down? Phosphorus? Yeah, phosphorus is. So if we follow all our structures, our steps, we can draw the Lewis structure for PCl5. Now, how many valence electrons, or how many electrons do I have around phosphorus here? How many altogether? 10. I've got 10. That's more than 8, isn't it? And by the way, how many electron domains are around this central atom? 5 electron domains. Very good. So I have 10 electrons around phosphorus. But we just did PCl3 earlier, didn't we? PCl3, that one only had 8. So when we say from the third shell on down that's true, they can have more than 8, but they don't have to have more than 8. So they can still have 8. Sometimes they'll have more than 8. Depends on their structure and who they're bonded with. Okay, so just follow the steps and you'll see which one has 8 and which one has more than 8. Okay, does that make sense? All right, so let's see if you can do a couple of these octets. Let's just take just a second and talk about This one with expanded octets, you know, the formal charges aren't very good, are they, on the structure on the left? But if we can move those electrons around, then we can get the expanded octets. This one, they're not sure that maybe this structure occurs more prevalently than this one, but how does that affect us? Well, we're just going to say that we expand the octet as necessary if it's the third row on down in order to help our formal charges be as close to 0. All right, so let's see if you can do a couple of these structures. Let's do, all right, I'll do one more. I'll do XeF4. Let's do that one, XeF4. All right, so let's go through and see how that process works with the expanded octet. So let's see. Let's do xenon has how many valence electrons? Yes, so how many would it have? 8. Okay, and then each fluorine, I know it doesn't really want to, but if we can pair it with fluorine, we can get a structure to form. Yeah. Okay, so how much does each fluorine have? Okay, so if I were to sum up the valence electrons, what are we going to get for that? Okay. 36 electrons. All right. So here's xenon. And then what am I going to do next? Okay, I'm going to put the 4 fluorines around here. Right? Then what? Make a bond. So how many electrons did I use up? Okay, 8. So subtract 8. What does that give me now? Okay, 28. All right, now what?
Let's do it again.
Yeah. All right, so we're going to complete the octet, right? So how many dots did I put around there? What, 24? So subtract 24. It gives me how many left? 4. And where do I go with leftover electrons? On the central atom as pairs. So I got to put it on xenon. You're like, whoa, that gives us more than 8. Yeah, well, xenon's in the below the third row, so we're good. So I'm just going to put him here on the corner in the diagonals, just like that. So there we go. How many electrons does xenon have around there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons. Wow, that's more than 8, but that's possible. How many electron domains, though, are around xenon, by the way? 1, 2, 3, 4, 5, 6 electron domains. Exactly. All right, do you see how that works? Okay, so let's do another one. I want you to do ICl2 minus this time. Do ICl2 minus. How many electrons are we talking about? Okay. Okay, so I have 22 electrons. I put 4 in the bonds, right? Okay. So subtract 4. That gives me 18, right? Now what's the next thing you're going to do is what? Peripheral? 12? 12 around the peripheral?
Yeah.
Okay, so 18 minus 12 is 6. And what do I do with those 6? They go on the central atom. So 1, 2, 3, 4, 5, 6. And there you go. So did you get that? Yay! Okay, so now we can do more than an octet. We can do less than an octet. So we can do all those things. Yay! So we can draw our Lewis structures. Awesome! Okay, well, we've got bonds here, right? We've got bonds in our Lewis structures. Okay, so let's talk a little bit about those bonds. We've talked about single bonds, we've talked about double bonds, and we talked about triple bonds. So are they all the same? No, they're different. So bond enthalpy is the energy it takes to break a bond. And when I mean a double bond, that means we broke both of those. Okay, a triple bond and we broke all 3, right? Okay, so this is the energy to break those bonds. And then this is the bond length. So what can you tell me? Oh, bond order. You know what bond order is, right? Single bond is the bond order of 1. Double bond is the bond order of 2. Triple bond is bond order of 3. So how does the bond order relate to the energy it takes to break it? Directly proportional. So what does that mean? As the bond order increases, what happens? The energy it takes to break it increases, right? So that bond's getting stronger, right? Okay, what about bond length? It's decreasing. So in other words, as we get to be more bonds, it's like we're pulling in closer and stronger, right? The bond length is decreasing and the strength is increasing. So it varies with our type of bond. Not only that, but it also varies with the sizes of the atoms. So we have all these different bond lengths. And if you look at ozone, remember we said, oh, that double bond was smeared over all of this? So it wasn't really a single bond, it wasn't really a double bond. So if you look at the bond length, it's kind of in between that, isn't it? So that double bond is smeared all over that, and we'll talk more about resonance and our other models as we go. But so those are the different bond lengths. Now we also have different bond enthalpies. So here we have, of course, the more multiple bonds we have, the more it takes to break more energy it takes to break all those bonds. Great. Well, what can we do with that? Well, we could figure out another way to determine the enthalpy of a reaction. Yay! Remember that in chapter 5? We did Hess's laws. I know, it's like, yes, it's enthalpy is back again. Woo! We did Hess's law. We did calorimetry. Your heats of formation. Well, now we can do this one. Yay! It's like, oh, man. Yes. So how do we do that? Well, if you break a bond, doesn't that take energy? Okay, so that's positive, right? And if you form a bond, that's the opposite. So it's going to be negative. Well, don't you have to have a reaction? You break and form bonds? Right? Okay, well, what if we added up all those energies? Then that's how we would get the enthalpy of the reaction. So this is our equation. Bonds broken. You add up all the bonds broken minus the enthalpies of all the bonds formed. So there it is. All the bonds broken minus all the bonds formed. That's our enthalpy of reaction. Now, in order to know whether that was a single bond, a double bond, or a triple bond, guess what you have to draw? Lewis structure! That's right, that's right. And it's important that we nail down the Lewis structures, because if you get the Lewis structure right, then you'll get this correct. And later on, we're going to be talking about shape. Well, that's based on Lewis structure. And then we're going to be talking about polarity. Well, guess what? That's based on Lewis structure and shape. So if you got the Lewis structure wrong, then your shape is wrong, and then your polarity is wrong, and your hybridization is wrong, and we're in trouble. Okay, so we need to nail down Lewis structures very well. So here we have our bonds broken minus our bonds formed. So let's take a look at that one. That's this right here. So if I had this reaction, okay, I have CH4 and I have a chlorine. I want to get one of the green balls onto the yellow over here to place a yellow one. So what am I going to have to do to make that happen? What would I have? I'd have to break which one? The green ones? Okay, break the green ones. And then, oh, and then you said we had to break which one? One of the yellow ones? Okay, great. Now, if I want to put them together, if I want to put these together, what do I have to do? I want to form, okay, so I broke two bonds, and now I want to form them, right? So what am I going to form? A carbon and a chlorine together? Great, thank you. And I need HCl, so don't I need to form this bond? So did I break all of them? No. So what we're going to do is count the ones we broke and count the ones we formed. So we would say, this is one that was broken, this is the one that was broken, this was formed, and this was formed. We go to the table and you look up that number. Okay, and you look up that number, and then we calculate that. So we take bonds formed and bonds broken. So you say bonds broken minus the bonds formed. So I would take those numbers, you see that? Bonds broken minus the bonds formed, and I would take that and I would write that out. Okay? All right, so what I think I want us to do next is I want you to, there's your numbers, so I want you to think about the bonds broken minus the bonds formed and calculate what that would be. Okay, so you want to add those all up. Bonds broken minus bond formed, so we'll do that. And we'll work on that during the break, and we'll come back at 1 and we'll keep working in Chapter 8, so you can take that break and work on that.